Okay, so I'm going to have a go at doing this the way I would like you to approach the question in the exam. So the first thing you do, step 1, is you read the question. Step 2, you read the question again. So read question again. Step 3, you draw it out. Step 4, you write down everything you know. And then step 5, we start going from the known, what we know, to the unknown. Okay? So this is what I'd like to do. The first thing, read the question. A skydiver jumps from an aeroplane and accelerates until she reaches terminal velocity. At a time t1, she opens a parachute and a second lower terminal velocity is reached before landing safely at time t2, which is here. Okay. The acceleration time graph for the motion of the skydiver is shown. Explain the shape of the graph. You should refer to the forces acting on the skydiver. There's 6 marks for this. I'm going to read it again. Have a little drink of water. So the skydiver jumps from an aeroplane and accelerates until she reaches terminal velocity. Now this is the acceleration and this is the time. Okay. At the time t1, she opens her parachute and a second lower terminal velocity is reached before landing safely at time t2, which is here. Okay. The acceleration time graph for the motion of the skydive is shown. Important, this is an acceleration time graph, which is quite unusual. Normally we would get velocity time or distance time. Explain the shape of the graph. You should refer to the forces acting on the skydiver. Right, so that's 1 and 2. Now we're going to draw it. Now we're going to draw, first of all, we're going to put the information at the various stages. This beginning is important. Then this is an important thing because at this point the acceleration has gone to 0, which means that this is the first time she reaches terminal velocity. To remember, terminal velocity means that the velocity is not changing, so the acceleration is 0. Opening the parachute, yep, that's obvious what happens there. That's here. Opening the parachute there. Reaching a lower terminal velocity here. And then nothing happens. She lands safely. So I'm probably going to choose an extra point there. And I'm going to suggest that there are 5 different sections. And I'm going to draw each one. At the very beginning, I'm going to draw each one. And I'm not going to try and use words to explain the shape of the graph. I'm going to refer to the forces. So I'm going to draw 5 little force diagrams. 1. At the beginning, this is a free body diagram. So this is the person. What happens at the very beginning is that there's only ever 2 forces involved in this. There's the downward force, which is always the same, weight, and the upward force, which is the drag. At the very beginning, the drag is almost 0. At start, drag, which is proportional to velocity. Now, technically, you might say it's proportional to velocity squared. You don't really need to say that. Just proportional to velocity is fine. That is going to, at start, d is proportional, is very small. mg is very much bigger than d, so therefore, large acceleration. Two, changing colour. Why not? You can do that digital. How much space have we got? Plenty of space. 2. What's happening here is that the gradient, this acceleration time, well, you can see that the slope of the graph is getting less. So that means the acceleration is decreasing. And the acceleration overall is decreasing because the drag is increasing. mg is always the same. Drag is increasing. after some time, and I'm probably going to say less than T1 because I want it to be clear that it's less than T1. mg is greater than d, but not hugely greater. D is increasing since velocity is increasing. Now, at a third point, I am going to change colour again and say point number 3 here. This is a significant point because the acceleration has dropped to 0. So if the acceleration drops to 0, let's mark these forces mg and d. mg is always the same, but this time d must be equal to mg. Now, mg is equal to d, since acceleration is 0 on graph. This is the terminal velocity. And this is a high terminal velocity that she reaches before she opens her parachute. Now mg is equal to d. We know mg is equal to d because the acceleration is 0 on graph. Terminal velocity. And so that's all we need. At 4, let me go back to pink. 4, she opens a parachute. And what happens is very interesting here. mg is always the same, but all of a sudden, d is enormous. Now, d is very much greater than mg. This is increased surface area of falling body. The parachute's opened, which has a massive increase of surface area. Increased surface area of falling body due to opened parachute. Right, this means what? That the acceleration is negative and very large. So this corresponds in the motion to a sudden deceleration. And then part 5, which I'm going to change colour to, go back to blue, I think. Sudden deceleration here. And then I think actually I'm probably going to put an extra region in. I'm going to change my mind on this. I'm going to rub out that one, and I'm going to put a 5 in here. And then what's happening now is that it's slowing down. So in terms of the forces, mg is always the same. Now drag is still bigger, but d is bigger than mg, but not very much bigger, since velocity has decreased. Velocity has decreased, therefore drag decreases. Drag decreases, gradually reducing negative acceleration. Then if you wanted to, 6 marks, 6 points. I mean, you've got all the marks here really, but what you could do is you could say 6 here And then at this point, it's the same as 3. And now mg is equal to d. Finally, when velocity decreases sufficiently or enough, mg is equal to d again, which is terminal velocity 2. No further deceleration. And the interesting thing, they're not really asking for this, but the mg, the drag force at terminal velocity, d, let's call this d2, and let's call this one d1. These d2 is equal to d1. Must be, because it's equal to the weight, mg. The only downward force, which is the only force that needs to be balanced by the upward force, the drag, is the weight. So the terminal velocities are different, but the drag forces are the same. And the way this works is that with a parachute, so for this terminal velocity, you've actually got a very big surface area, meaning that a low velocity times a high surface area can give you the same drag force as an individual falling down here. In this one, this has just the individual falling, and they have the parachute on their back, but they have mg down there, and this is the drag, and this is a high velocity times a low surface area. So you can get the same drag force in two ways. You can either have the thing moving very fast with low surface area, or you can have the thing moving more slowly but with a high surface area. And the problem is, if it's moving fast, it's, yes, fantastic, it's balanced the weight, but the problem, if you suddenly stop something moving at that high velocity, you're going to end up with a lot of damage. So the idea is that you want a huge surface area, so even a low velocity will match the weight. And that's how you do a question which could be quite difficult. You break it up into parts and you draw diagrams. Simple.